Hi, Mrs. KJ here, going over 5.08 Le Chatelier's principle. Le Chatelier's principle predicts the effect of factors that shift the equilibrium of a chemical reaction. Concentration, temperature, and pressure can affect the way a reaction proceeds. These factors can also disrupt the equilibrium of a reaction system, causing the equation to shift in favor of either the products or the reactants. This lesson describes how these factors change reactions. Goals for this lesson: explain Le Chatelier's principle, and if I'm saying it wrong, I'm sorry. Describe the conditions under which Le Chatelier's principle applies. Predict the effects of changes in concentration on chemical equilibrium. Predict the effects of changes in temperature on chemical equilibrium. Predict the effects of changes in pressure on chemical equilibrium. Chemical reactions are in chemical equilibrium that may be affected by the change in conditions, so temperature, pressure, etc., and they may be predicted by Le Chatelier's principle. So slide 2 will give you the study guide, and from the study guide I just copied the beginning and Le Chatelier's principle. Factors such as changes in pressure or concentration will affect the equilibrium of a system in predictable ways. In equilibrium, a balance exists between the amount of reactants and products. Some reactions produce very little product. Others go almost all the way to completion, meaning there's like 99% product and 1% reactants left over. And when I say left over, remember how we said it was dynamic or moving? So that 1%, it changes back into the reactant, but then that changes into the product, and some of the product changes back into the reactant. It goes back and forth. At some point, however, under given conditions, all reactions reach equilibrium, the state of balance between products and reactants. But a system's conditions can change, and with them the nature of the reaction's equilibrium. Think about when we talked about dissolving. When can you dissolve more sugar in water? If the water is cold or hot? You can dissolve more if it's hot. Okay? So it's the same idea. The equilibrium can change when there's different conditions. Henri Louis Le Chatelier was a French-Italian chemist who worked in the late 19th and early 20th centuries. His most famous work involves equilibrium reactions. He developed a qualitative idea that chemists use to determine how changing the conditions of a system will change the equilibrium of a reaction. That idea is called Le Chatelier's principle. Le Chatelier's principle states that any change to a chemical system at equilibrium causes the reaction to move in the direction that will minimize or offset the effect of that change. So I copy-pasted that sentence, saying that Le Chatelier's principle states that any change to a chemical system at equilibrium causes the reaction to move in the direction that will minimize or offset the effect of the change. So move in the direction means if it shifts to the right, you have more products. If it shifts to the left, you have more reactants. So that's what they're talking about with moving direction. Equilibrium is similar to a balance. When you add products to a system at equilibrium, suddenly there is an excess of product. The system is out of balance and needs to get rid of the excess. As a result, it uses some of the new products to make reactants, or in other words, to go back into reactants. The product concentration goes down and the reactant concentration goes up. When the system reaches equilibrium again, all the concentrations are different from the previous time it was at equilibrium, but it is again at equilibrium. There are more reactants than before, but also more products. The ratio of the products and reactants, meanwhile, is back to where it started. An optimal balance between reactants and products always exists for a given reaction. But remember, they don't have to be 50-50. Okay, it's not a 1-to-1 ratio. They can be 99% and 1%. It's just all about the balance as far as what percent are changing into reactants, what percent are changing into products. An equilibrium can shift to the left or to the right. Once a reaction system is in equilibrium, it will remain in that state unless the system is disturbed. One way to disturb the system is to add or remove reactants or products. Chemists talk about the equilibrium shifting. If more products are formed, then the equilibrium has shifted toward the product side. Because it is on the right side of the equation, you say equilibrium shifts to the right. So we talked about that in 5.07 recording. So if it's shifting to the right, that means more products are being formed. If more reactants form, equilibrium shifts to the reactant side or to the left. And then they give a flow chart to kind of talk you through it. And so we have AB are turning into C and D. And of course, C and D can turn back into A and B. So we have the system in equilibrium. What if reactants are removed? Okay, well, if you didn't, then it's still in equilibrium. But let's say we took out some of the reactants. This causes fewer products. Shifts equilibrium to the left, okay, and it produces a system in equilibrium. The same thing with reactants added. Well, no, if you don't add or take anything, then it stays at equilibrium. But what if you add reactants? This causes more products. Notice how the arrow is bigger to the right? Whereas here, when we had fewer products, that means more reactants, and the bigger arrow is to the left. So let's go back. We have reactants are added, yes. It causes more products, shifts equilibrium to the right. And then it produces, again, a system in equilibrium. A chemical equation can shift to the left or to the right as conditions change. So we haven't taken notes yet because I kind of wanted to get to here because it has this nice table here. So one of four things can happen. If you add reactants, equilibrium shifts to the right or towards the product side. So think about it. You have more beginning stuff. Well, if you have more reactants, what are they going to do? They're going to form products, right? You already know that. Okay, so we said add more reactants. Okay, put more baking soda and vinegar together. You're going to get more bubbles, right? It's shifting to the right. It's making the product. What if you remove the reactants? Now equilibrium shifts to the left. Okay, so you don't have as much. And what's going to happen here in a reversible reaction, the products are going to say, oh, we don't have enough reactants. Here, let's break down to make some more reactants. Let's balance this back out. So it shifts to the left. If you add products, okay, so again, we have more over here on the product side. It's going to shift it to the left. It's going to say, here, there's too many of us over here. Some of us need to break down and become reactants again. If you remove products, okay, so we got rid of the products. So now we have more reactants. It's going to shift to the right. A system will react to produce equilibrium. The table shows all cases of changing the concentrations of reactants or products. Think of it like a big teeter-totter. Okay? If you have too much on this side, it's going to make more products to balance it out. If you have too much products, too many products, it's going to shift it to the left and make more reactants to balance it out. It's all about balancing. All right, so I added the table to the notes, and I put, remember, it's like a seesaw, and if it's too heavy on one side, some of the chemicals slide to the other side to regain the equilibrium. And I'm going to put equilibrium because, remember, in this case, balance does not mean 50-50 or a 1-to-1 ratio. Balance could mean 99% products, 1% reactants, and the reason it can be that is because that's the point that you have the equal amounts all the time. Remember we looked at the graphs in the 5.07 lesson, and when the concentration of products leveled off on the graph and the concentration of reactants leveled off on the graph, that's when you hit equilibrium. Equilibrium reactions can regain chemical reactions can regain their equilibrium. A reaction that can be shifted forward or backwards, that is to the right or to the left, depending on the concentration of the reactants and products. Consider what would happen if, at the point where a reaction is at equilibrium, more reacted were added to the system. So in other words, we dumped a bunch of reactants into the cup. The equilibrium would become disrupted. Obviously, right? You added more baking soda and vinegar, you're going to get more bubbles. The reaction would continue to use up the new additional reactants until equilibrium was reached again. Alright, so here they show concentration. So we have a lot of reactants at the beginning and not as many here because remember they turn into products. We don't have any products to start with and more products are being formed. Normally equilibrium concentrations are reached for reactants and products. But now, boom, look what they did. They dumped in some extra baking soda and vinegar. Well, what's going to happen next? Hit pause, think about it. And when you have more reactants, obviously you're going to make more products, but then after a while, again, it's going to level off. So you can see it basically has that same slope as before, that same angle of your slope as before, and that's because, again, it reached equilibrium. The converse would also happen. If some of the product or reactant were removed from the system in equilibrium, then the concentrations would change. The only way the system could return to equilibrium would be to produce more of the substance that was removed. So I added to our notes, if the chemical reaction was at equilibrium and more reactant was added, then obviously more product would be formed, right? But the main idea here then is that equilibrium would be reached again. Look at the example of how concentration changes can shift equilibrium. Smog forms when nitrogen dioxide, a brownish gas, is converted to N2O4, a colorless gas. What happens to this equilibrium if more NO2 is added to the system? Le Chatelier's principle provides an explanation of what will happen. As the NO2 is added, the system first shifts to the right. Okay, and if it's shifting to the right, that means there's more what? More product is being formed. Soon the reaction will again be in equilibrium state. Conversely, if more N2O4, so more of the product was added to the system, then the reaction would shift to the left, consuming the N2O4 and producing more of the reactants, the NO2. So here it shows adding reactants drives the reaction to produce more products, taking reactants away will have the opposite effect. So reactants, we start out with a whole bunch, it's changing into the product, then boom, we added some more, and it changes back into product again. We have product being formed, we're leveling off, but oh, they added more reactants, so now more products can be formed. Temperature also works to shift the equilibrium in a chemical reaction. An increase in temperature may cause some reactions to proceed more completely to the product side. In other reactions, an increase in temperature may make the reaction slow down and not proceed as completely to the product side. Look at an example to see if you can predict what will happen as temperature increases. Hydrogen and iodide react to form hydrogen iodide in this chemical reaction. So, concentration of products and reactants over time for H2 plus I2 yields 2HI plus heat. We have our concentration and our time. Removing heat from the system is like removing a product. Okay, because look, we produce heat. So if we take away heat, it's like removing the product. The reaction is driven to the right according to Le Chatelier's principle. Alright, so the concentration of our reactants goes down as concentration of product goes up. Then the temperature is decreased, so it gets colder. Now look, we have less and less of our reactant, and we still have more of our product. So in this case, we took away heat, we have less of the product, and so in order to have equilibrium, then more of the product needed to be formed. So how to change reactions? The first way is temperature. Temperature can increase or decrease a reaction. It really depends if it's exothermic, because if it's exothermic, heat is out, so heat is a product. Or if it's endothermic, and heat is a reactant. Pressure also affects a system's equilibrium. Reactions involving gases are particularly sensitive to changes in pressure. A way to change the pressure on a gas reaction system is to change the volume of the container holding the gases. Look at the smog example, where NO2 becomes N2O4. What will happen if the pressure on the system is increased? According to Le Chatelier's principle, the system will seek to balance the increase in pressure. The system favors any shift that balances the increase in pressure. Since there are 2 moles of gas on the left and only 1 mole on the right, okay? And that's because of the balance equation. So we have 2 molecules or 2 moles of NO2 for every 1 mole of N2O4. So we're using the coefficients. Since there are 2 moles of gas on the left and only 1 on the right, the system will respond to an increase in pressure with a shift to the right, compensating for pressure increase. So again, here's our pressure increase line. The reactants go down and continue to go down. The products go up and continue to go up. I added to the notes number 2, pressure, especially if gases. Look at the coefficients to see how many moles molecules are on both sides of the equation. Here's our example. There are 2 moles of reactants and 1 mole of product. An increase in pressure will cause a shift to the right or more products formed because the reactants are being squished together. And we will continue in part 2 of the videos.